So in 1781, an English composer, technologist, and astronomer called William Herschel noticed an object on the sky that didn't quite move the way the rest of the stars did. And Herschel's recognition that something was different, that something wasn't quite right, was the discovery of a planet, the planet Uranus. A name that has entertained countless generations of children, but a planet that overnight doubled the size of our known solar system. Just last month, NASA announced the discovery of 517 new planets in orbit around nearby stars, almost doubling overnight the number of planets we know about within our galaxy. So astronomy is constantly being transformed by this capacity to collect data. And with data almost doubling every year, within the next 2 decades, we may even reach the point, for the first time in history, where we've discovered the majority of the galaxies within the universe. But as we enter this era of big data, what we're beginning to find is there's a difference between more data being just better and more data being different, capable of changing the questions we want to ask. And this difference is not about how much data we collect, it's whether those data open new windows into our universe, whether they change the way we view the sky. So what is the next window into our universe? What is the next chapter for astronomy? Well, I'm going to show you some of the tools and the technologies that we're going to develop over the next decade, and how these technologies, together with the smart use of data, may once again transform astronomy by opening up a window into our universe, the window of time. Why time? Well, time is about origins, and it's about evolution. The origins of our solar system, how our solar system came into being. Is it unusual or special in any way? About the evolution of our universe, why our universe is continuing to expand. And what is this mysterious dark energy that drives that expansion? But first, I want to show you how technology is going to change the way we view the sky. So imagine if you were sitting in the mountains of northern Chile, looking out to the west, towards the Pacific Ocean, a few hours before sunrise. This is the view of the night sky that you would see. And it's a beautiful view, with the Milky Way just peeking out over the horizon. But it's also a static view. And in many ways, this is the way we think of our universe, eternal and unchanging. But the universe is anything but static, constantly changes on timescales of seconds to billions of years. Galaxies merge, they collide at hundreds of thousands of miles per hour. Stars are born, they die, they explode in these extravagant displays. In fact, if we could go back to our tranquil skies above Chile, and we allow time to move forward, to see how the sky might change over the next year, the pulsations that you see are supernova, the final remnants of a dying star, exploding, brightening, and then fading from view. Each one of these supernova 5 billion times the brightness of our sun. So we can see them to great distances, but only for a short amount of time. 10 supernova per second explodes somewhere in our universe. If we could hear it, it would be popping like a bag of popcorn. Now, if we fade out the supernova, it's not just brightness that changes. Our sky is in constant motion. This swarm of objects you see streaming across the sky are asteroids as they orbit our sun. And it's these changes and the motion, and it's the dynamics of the system that allow us to build our models for our universe, to predict its future, and to explain its past. But the telescopes we've used over the last decade are not designed to capture the data at this scale. The Hubble Space Telescope, for the last 25 years, it has been producing some of the most detailed views of our distant universe. But if you tried to use the Hubble to create an image of the sky, it would take 13 million individual images, about 120 years to do this just once. So this is driving us to new technologies and new telescopes. Telescopes that can go faint to look at the distant universe, but also telescopes that can go wide to capture the sky as rapidly as possible. Telescopes like the Large Synoptic Survey Telescope or the LSST, possibly the most boring name ever for one of the most fascinating experiments in the history of astronomy. In fact, proof, if you should need it, that you should never allow a scientist or an engineer to name anything, not even your children. We're building the LSST. We expect it to start taking data by the end of this decade. I'm going to show you how we think it's going to transform our views of the universe. Because one image from the LSST is equivalent to 3,000 images from the Hubble Space Telescope. Each image 3.5 degrees on the sky, 7 times the width of the full moon. Well, how do you capture an image at this scale? Well, you build the largest digital camera in history, using the same technology you find in the cameras in your cell phone or in the digital cameras you can buy in the high street, but now at a scale that's 5.5 feet across, about the size of a Volkswagen Beetle, where one image is 3 billion pixels. So if you wanted to look at an image in its full resolution, just a single LSST image, it would take about 1,500 high-definition TV screens. And this camera will image the sky, taking a new picture every 20 seconds, constantly scanning the sky, so every 3 nights we'll get a completely new view of the skies above Chile.